Okay, students, hello again. This is our Chapter 8 video, and this one is kind of an extension of Chapter 7. We're going to do some stuff related to chemical reactions, and we're going to do some expand on that and do some other things too. But basically, it's kind of like aqueous chemistry. All this stuff is solution chemistry. And the first thing that we'll go over is solution concentration. That is what is the first thing in your book and the first thing we're going to tackle. A couple of things I'll do is dilution, electrolytes, acids and bases, precipitation, and redox. So that's most of the topics. There's a few other topics I won't hit on. And once again, there's a lot of topics here. I'll just be introducing most of them, some of them very briefly, and others I'll spend a little more time on. For our solution concentrations, there's lots of options. You can do like percent concentration. You can do things like mass per unit volume. But because it's chemistry and because this is the best way to represent things, we typically use moles. So moles of solute per liter of solution, that is molarity with a capital M. It's liters of solution, not of solvent. So remember, the solute plus the solvent gives you the solution. Equals, I guess I should put. Solution is the whole thing. The solute is the one that's present in smaller amount. And the solvent is the one present in larger amount. So when we deal with aqueous systems, the solute here is sodium chloride, and the solvent is the water, and then we have a salt solution. So it's very simple. You know what moles are? It's just moles per liter of solution. That's all there is to be say about that. We'll do some example calculations in class. You'll be expected to calculate the molarity, but you'll also be expected to back calculate if you're given the molarity. Hey, how many moles are in there in this given volume, or how much volume is with this many moles. So that's also fair game. So one of the things that's really important is dilutions. One example your book gives is, when we do this a lot in my lab, we get standard solutions. And this is a perfect example of one of lead. If you're doing water quality testing, you want to know about lead or something like that, you might get a standard from EPA. And that means that we can run our methods and run it through our instruments and make sure that we get whatever concentration EPA says is in that bottle, But most of the time you're going to dilute it down because it comes very concentrated. So because with a dilution, all you're doing is adding water, the number of moles stays the same, right? That's all I'm doing. The moles of lead, if I take a portion of this solution out, and I put it into a beaker, and then I add some water also, the number of moles here is equal to the number of moles here. All I did was dilute it. So there's the same number of moles in a larger volume. So the initial moles is equal to the final moles. Using that and knowing that molarity is moles per liter of solution, just kind of saying that, just kind of cross-multiplying here, we now know that moles is equal to molarity times volume. Looking at your units, that's moles per liter times liter equals moles. So you can use that idea to say that the initial volume times the initial molarity equals the final volume times the final molarity, because that's moles equals moles. So you can use that process, and we'll do some example calculations using that. It's a very useful equation. Okay, we'll do some of those in class. Now, practically speaking, in the lab, the way you do dilutions and the way you make up solutions in general is, this is a volumetric flask right here, and it'll have a mark to where the total volume needs to go to. And what you typically do is you add some water, say water's our solvent, and then add your salt also, and you get it to dissolve. You don't add the total amount of volume. So if you're making up a 1 liter solution, you don't put 1 liter of water in there and then add your salt, because the reason is that salt takes up space and your solution will be greater than 1 liter. So what you do is you might fill it up to, say, 500 mils, whatever, add your salt, get it dissolved, and then you carefully, if you will, bring it up to volume so that your total volume is 1 liter. You don't use a liter of solvent, okay? That's one of the keys to making up a solution. And as we deal about solutions, we talk about solutions, there's things called electrolytes that we need to define and talk about. Strong electrolytes are things that completely dissociate in solution and create a lot of ions. So they're going to create lots of ions in solution. Okay? And we can measure this by they'll be able to conduct electricity. Because electricity really is movement of electrons. And ions are charged species. So basically, they can carry that charge of electrons across the solution and to complete your circuit. So the idea is that this light bulb would not light if it was just in the air. But once I lower it into the solution, we complete the circuit. And those ions can carry that charge. That's what a strong electrolyte is. A weak electrolyte produces very few ions. And therefore won't light a light bulb, or will light a light bulb very dimly. I've actually done, demonstrations for middle school kids and things like that, where I can take a solution, show them that it doesn't, of water, pure water, and even tap water will not light a light bulb. I can add a little salt and it'll light it dimly. I can add a little bit more salt and it'll light it brighter. You can get that. Okay? Non-electrolytes are going to be substances that produce no ions. And obviously your molecular compounds, that's supposed to be an arrow, don't produce any ions. So if I dissolve, say, carbon dioxide in water, well, I don't get any ions. If I dissolve sugars are molecular compounds. Glucose is C6H12O6. There's no way for you to know by looking at that, but it's a molecular compound with no metal, so it doesn't ionize. Now, there are some molecular compounds that ionize in solution. They're acids, and they're going to be organic acids, molecular acids. And they will produce ions in solution. There's no way for you at this point to know that by looking at them. Once you take organic chemistry, you'll get a better feel for that. And if something has very little solubility in water, then it can't be a strong electrolyte because it can't produce a bunch of ions. And I'll talk about that at the end of the chapter. So here's our acids. And the Bronsted-Lowry definition is just one definition of acids and bases. But this is the one that you need to be most familiar with right now. Acids are proton donors. But I also like to use the Lewis definition too and say they're electron acceptors. That'll come in handy later. Probably not even in Gen Chem. I don't hold you responsible for that now, and I'm not even sure your chapter talks about it. The old textbook did a little bit. They talk about it at the end of the textbook in a different chapter. Bases are proton acceptors or electron donors. The electron is the better definition because it applies to all things, where the protons don't always. Because there are species that don't have any protons that are acids. But for right now, we can think of it as in this particular reaction up here you're looking at, hydrochloric acid donates its proton to water. In this case, water's a base. It picks up that proton. Water is what we know as amphoteric. And that's discussed in your book, and we'll talk about it in class. It can act as either an acid or a base, depending on the partner it's paired with. Okay? So here, that hydrogen right there is being donated to the water, and we're left with the chloride ion. This is a strong acid, and it will be actually a strong electrolyte, producing lots of ions. Even though there's no metal here, hydrogen kind of is in group 1 and behaves kind of like a metal. So neutralization reactions is when we add an acid and a base. Sodium hydroxide is a base. It's going to, the hydroxide is going to accept that hydrogen and form water. And then we got the salt forming. This is a molecular equation. Okay, it doesn't show the ions. We'll go over in class what an ionic equation is, an overall ionic equation, and a net ionic equation. This is the molecular equation, just showing you the molecules. And a neutralization reaction always produces a salt and water. Salt is a general term where the cation comes from the base and the anion comes from the acid. We all know sodium chloride as kind of the salt, but there's lots of salts. So you'll need to memorize strong acids, and there's not a lot of them that you're responsible for, and here they are. You want to memorize them because anything else that's not on that list, you're to consider a weak acid. Okay? There are other strong acids, but they're not that common. And for you guys, we just say, okay, if you memorize these, then you know that everything else is weak. Strong acids are strong electrolytes. They completely ionize in solution. So if I was to analyze the solution, once I've added it to water, I find very little of this present. Where weak acids, acetic acid's the classic you're going to see a lot of, so get familiar with it. That means if I analyze the solution, I'm going to see a significant amount of this still in solution. Now remember, this is the shorthand way of writing acids and bases. The H positive always combines with water, like we saw up here. This is the correct way of writing it. The shorthand notation is HCl goes to H positive plus Cl negative. But that's not really what happens, because that's just a proton. A hydrogen ion, right, that's lost its electron is just a proton, and protons just don't exist in general chemistry, only in plasmas. That's just a charged species like that. It's just a proton. I mean, it's a subatomic particle. So that's got to associate with something, and it will associate with water, and that's what happens. It's much more stable associating with H2O than it is being kind of naked. In plasmas, stars, things like that, you can find just protons flying around. And we can equate this with strong bases and weak bases also. Strong bases completely ionized. Once again, this is the shorthand notation of writing it. And here's a weak base. And we also use this double-headed arrow to show you that, there's still a lot of this left, where one-headed arrow means, hey, the reaction lies heavily to the right. We have very little of this left over. We did the same thing up here. Double-headed arrow, single-headed arrow. That's why we do that. So we need to now take a look at precipitation reactions. And in a precipitation reaction, the product has limited solubility. So in this case, we have two species reactant, lead nitrate and sodium iodide. Okay? And these are both aqueous, meaning they're present in solution. But when they get together into the same beaker, if you will, the same solution, they can form a species that doesn't like, if you will, to be as ions in solution. So you can see they basically just swap partners. The lead and the iodide swap. The nitrate and the iodide ion swap, and you get the lead iodide and the sodium nitrate. Now, sodium nitrate is still very soluble. So we get this yellow precipitate. That's what you see here. And you have to learn to be able to predict these, and you do that by basically learning some of your solubility guidelines. So once again, your exams are open book, open note. There's no memorization here, but you need to start getting familiar with this, because you don't want to be looking at this chart in great detail and trying to figure it out while you're taking an exam. So start to get familiar with the ones that are insoluble. And we'll talk about this a lot in class and do some examples. And your book gives a nice little matrix, too, that kind of summarizes and pulls this all together. So moving on, we have just real quickly defining two types of solutions. I probably should have eliminated the slide, something you can just read. Or what a saturated solution is supersaturated. The way you can make a supersaturated solution is you can raise the temperature, because the solubility of solids is greater at high temperature, and then slowly lower it, and you wind up with a supersaturated solution. And then when you drop a little crystal in there, it causes it to crystallize and all come out of solution. You can read about that. The last thing I want to talk about is oxidation reduction reactions, and learn the definitions of these. Oxidation, the best definition is loss of electrons, but you can also look for things like increase in oxygen content. The electron definition applies to everything. Gain of electrons. You might think that's confusing. Reduction, the gain of electrons, it sounds like reduce. And it is, but it has to do with the oxidation number, which is the next slide. You see a reduction in the oxidation number. That's where that comes from. Don't get confused by that. The oxidation number is kind of just like a theoretical charge that exists. And this is a table you're going to want to become very familiar with. And we're going to talk about this. So start to review this table and get a feel for how to identify and assign oxidation numbers. And you can do this within molecules, and then you can start to look at chemical reactions and decide, hey, what's the oxidation number? What's being oxidized and reduced, right? And actually, how many electrons are being transferred and where they're being transferred. That becomes really important for things like understanding stuff like rust is what you're seeing here, but also designing batteries, using different metals for batteries, and understanding that reduction potential, and lots of applications there. And oxidation reduction reactions are one of the big groups of reactions. Many of the reactions inside your body are redox, what we call redox reactions. Many reactions in the environment are redox reactions. So just get familiar with those. With that, I think I've introduced what I wanted to do and set the stage for us to tackle this in more detail in class. So that's the end of the Chapter 8 video.